In this video, we're going to talk about normal distributions, which is a type of continuous random variable. So a continuous random variable has a normal distribution if the graph of its probability distribution is symmetric and bell-shaped and can be described by this equation. Y equals 1 over sigma times the square root of 2 pi times e to the negative half times x minus mu divided by sigma all squared. So this formula is a little intense. We won't really be using it directly, but one thing I wanted to point out with this formula is that this formula just changes based on the mean and the standard deviation. So the mean mu is the mean and sigma is the standard deviation. And recall that the mean is the center of the distribution and the standard deviation is the amount that the data is spread out. So if sigma, the standard deviation, is large, then the data is more spread out. If sigma is small, then the data is packed more close together. So many sets of data, especially naturally occurring sets of data, are modeled or fit a normal distribution, just with different means and standard deviation. So if we look at any test given to a large set of people, or the weight of any animal, or the lifespan of a species of animal, or many other naturally occurring data sets, these will have a normal distribution, and we'll talk about why that's true when we talk about the central limit theorem in a few lectures. So again, the mean and standard deviation is the thing that changes from one normal distribution to another. So below are two different normal distributions. The first is describing lengths of pregnancies for humans, and that distribution is normally distributed with a mean of 268 days and a standard deviation of 15 days. And so here is the mean, mu, and it's the center of the distribution. It should be the highest point on the curve. This other distribution has a mean of 162 grams. So again, this is our mean. It should be the tallest point on the curve, and it's the center of the data. And this has a standard deviation of 0.8 grams. So if we go over 8 units to 170, we have one standard deviation above the mean. Over 8 units to 154, we have a standard deviation below the mean. So this is the mean plus one standard deviation, the mean minus one standard deviation. And because the standard deviation is smaller than that for the lengths of pregnancies, here the standard deviation is 15 days, this data is more spread out. So recall that for a normal distribution, 68% of data is within one standard deviation of the mean. And so in both cases here, 68% of data is within one standard deviation of the mean. The data is packed more tightly together with the standard deviation of 8 grams than it is for the standard deviation of 15 days. So here's a thought experiment. What mean and standard deviation would make the equation describing a normal distribution as simple as possible? So we're looking at this equation and saying, okay, what number could we plug in for mu? What number could we plug in for sigma in order to simplify this equation? So we see that a sigma is here, and the mean is here. What number could we plug in for that to simplify this equation? So if we chose to plug in mu equals 0 and standard deviation is 1, the mean is 0, the standard deviation is 1, then look at what happens to this equation. So for a 1, this just disappears and becomes just 1 over square root of 2 pi, because 1 times something is just itself. And similarly, dividing by 1, this goes away here. There is no longer a sigma in the denominator. Mu is 0, x minus 0 is just x, and so x minus mu goes away as well. So we now have a simpler formula. Z is equal to 1 over the square root of 2 pi times e to the negative x squared over 2 for this, what's called the standard normal distribution. So a normal distribution with a mean of 0 and a standard deviation of 1 is called a standard normal distribution. And again, its mean is at 0, so that is the mean, and the standard deviation is 1. So that is the standard deviation and the mean. And one thing that's really neat about the standard normal distribution is that the values in a standard normal distribution are already z-scores. So if we had like a data value of, 1.5, that would already be a z-score. It is 1.5 standard deviations above the mean. So this is z equals 1 standard deviation above the mean, z equals 2 standard deviations above the mean, z equals -1 is 1 standard deviation below the mean, and so on. Recall that a z-score is the number of standard deviations a data value lies above or below the mean. So a standard normal distribution is special because its data values are already z-scores. And because of that, we usually use the variable z for a standard normal distribution rather than the variable x. So suppose, for example, that the temperatures of freeze pops are normally distributed with a mean of 0 degrees Celsius and a standard deviation of 1 degree Celsius. What is the probability then that the temperature of a randomly selected freeze pop is between -1 and 1 degree Celsius, between -2 and 2 degrees Celsius, and more than 0 degrees Celsius? So some things to help you start to think about this. Recall that this is a normal distribution and therefore it is symmetric. My drawing is not exactly symmetric, but the normal distribution should be symmetric. And the probability that z lies between any two values, a and b, is p, probability that a is less than z, which is less than b, is equal to the area under the curve of the probability distribution from z to a. So when we're talking about, say, the probability that the temperature of this freeze pop is between -1 and 1 degree Celsius, that's also the area under this curve. This is the probability that -1 is less than z, which is less than +1. So think about those just for a moment and we'll talk about them. Okay, so what is the probability that a randomly selected freeze pop is between -1 and 1 degree Celsius, assuming that these have a normal distribution with a mean of 0 and a standard deviation of 1? So this is, again, the standard normal distribution. It's called the standard normal distribution when the mean is 0 and the standard deviation is 1. And as we said, these are already z-scores. So this area in here between -1 and 1 is all within 1 standard deviation of the mean. So this is the mean plus 1 standard deviation and the mean minus 1 standard deviation. And by the empirical rule, we know that 68% of the data falls within 1 standard deviation of the mean. So what percentage or what probability? It's a 0.68 probability that our data value is between -1 and 1. And what about between -2 and +2 degrees Celsius? So a temperature of 2 degrees Celsius would correspond to the mean plus 2 standard deviations because the mean is 0 plus 2 times 1, that is 2. And a temperature of -2 would correspond to the mean minus 2 standard deviations. The mean minus 2 times 1 is the standard deviation. And so recall by the empirical rule that 95% of the data is within 2 standard deviations of the mean for normal distributions. So this is the empirical rule, which tells us the percentage of the data that falls within different numbers of standard deviations of the mean, the empirical rule. And so the probability that -2 is less than z, which is less than +2, is 0.95. So 0.95 is that probability. What about more than 0 degrees Celsius? So this is actually not using the empirical rule, but using the fact that the normal distribution is symmetric. So the normal distribution is symmetric about the mean, and because it's symmetric, that means that half of the data lies above the mean and half of the data lies below the mean because it is symmetric. So the probability that z is greater than 0 would be equal to 0.5. And in general, for any normal distribution, the probability that x is greater than the mean is equal to 0.5 for a normal distribution. So what if we wanted to ask a slightly different kind of question? What is the probability that the temperature is less than 1.78 degrees Celsius? So here's negative 1.78 on this scale, and we're looking for this probability, which corresponds to the area under the curve below negative 1.78. So this is something that we cannot just figure out from the empirical rule or from like the symmetric property of the normal distribution. Technically, the probability that z is less than negative 1.78 is equal to the integral of the function of the standard normal distribution. So that is the integral of 1 over the square root of 2 pi times e to the negative x squared over 2 with respect to x. This integral is not easy to take, even for those with calculus knowledge. We cannot use, for example, substitution or other easy integral techniques. So even those that can integrate typically don't do this, but they refer to a previously published table of values. So different ways people might do it are by using a table of values for the standard normal that have been previously calculated, or by using, a calculator that gives this value, or a website or a program that gives this value, because this finding probabilities for normal distributions is very common to need to do. Many distributions have a normal distribution, and when we talk about, say, hypothesis testing later on, in many cases for hypothesis testing, we need to find probabilities for normal distributions. So finding this is a very common problem that is typically solved either by a computational device or by a table. And in the next videos, we'll describe both ways of finding the probability for standard normal distributions as well as for normal distributions with any mean and any standard deviation.